Hello everyone. It's always nice to know what the steady state values are, but sometimes it's nice just to have a little look at what the graph actually looks like when you simulate it. So we've already got defined this function here in model Goodwin. So this is our system again. So if you recall, this is the same as our definition we had a minute ago. So dx by dt equals this equation, and dx by dt2 is this equation. Our parameters, you know we've got ki set to 0, so the inhibition constant is 0, so we don't expect any negative regulation at the moment. If you refer back to the original equations, that's equivalent to setting this to 0, and that's times by the x2, so that's all 0, and so we have no negative regulation in the system. So we have this function, but we need to be able to simulate it. So the way we do that is, and I'm going to do this in the command line, so I'm going to clear this, is using this ODE45 function. So we can run this, but this returns two things. So it returns t and x. And then we want to run ODE45. And now the first variable that goes in there is actually the name of the function. So in our case, that's at, which you have to append to the start of the name, model Goodwin 2. And then there's two other things we need. We need the time course, so we need the initial time and the end time, which we want to simulate the system for. So I'm going to choose 0 and 10. So we start at time 0 and we end at time 10. And also, we need some initial conditions. So here I'm going to say we have 0.1 of each of the... sorry, I'll make those a bit bigger. We have 0.1 of each. Okay? So if I run that, you can see that I've got a big output. So perhaps we want to run that and suppress the output this time. And now we can just plot. So simply by using the plot command, passing in the variable t and the variable x, which we just defined from the output of the ODE45 function, and we get something that looks like this. Okay, which is the how do I make everything bigger? Sorry, girls. That function. Okay. Okay, so you can see it. I'll click on each line, make them bigger. Okay, so we can see that starting from our initial value of about 0.1 for each species, we end up going all the way up to 100 for both. So clearly there's some bound to the growth, but it's not really showing what we want because we don't have the inhibition in. So let's see what happens when we change that inhibition to something like what we had before. So I'm going to close this again. And remember in the simulations we were doing before, when we had found the steady states, we were using an inhibition constant of 0.1. Okay. So if I save our model, and we go back and we're going to re-simulate what we had before. So calling this function again, this ODE45, with exactly the same time and initial conditions. And we'll plot that again. Okay. So now we have something different from before. I forgot to press hold on, and we should have shown you the difference between the two. I can go back and do that. So if I set this back to 0, save this, now type hold on, rerun the command once more. Sorry. Now you can see, so these curves that go up to 100 are the system without any inhibition. And these curves that are down nearer, well, we know about 3, are the curves where the inhibition is 0.1. So you can see the system is very different, depending on whether even having a small amount of inhibition. So if I get rid of these two large values, and so we can see what's going on in the small scale, let me make those bigger. Okay, so we converged to some steady state value, and that's about 3.1. If you recall, that's about what we had when we found the steady state of the system before. But actually, what happens is something more interesting before we get there. So actually, we overshoot that value for both of the x1 and x2 before actually coming down a bit and then reaching the steady state. So we've got a small oscillation here. So that's quite interesting to see, and so it's worth always plotting the time course of these things, even if you're interested in the steady state dynamics a long time. But I think I'll pass back to Gerald now, as I think that's all I have to say. So, thank you.
Thank you, Rob. So that's our final MATLAB function. And what we have now is some reasonable output for given values of the parameters that we have chosen. And what we can see is that feedback takes place immediately with certain characteristics given by combination of this constant that governs the strength of the feedback inhibition, in this case called Ki, the feedback inhibition constant, regulatory constant if you like, and multiplied with the amount of the second substrate x2 actually present. And if you remember from previous things, that's of course an important thing in signaling cascades or wherever you have consecutive reactions, whether you have metabolism going to end with ATP as an energy source, where ATP feedback regulates what's going on in early steps of glycolysis, or if you have signaling cascades that go through RAS-RAF and MAP kinases, where one of the important feedback regulators is the ERK protein, which is actually the protein that translocates to the nucleus and actually re-regulates gene expression there. So we have the feedback from that downstream signaling molecule to upstream events. And a similar principle in many, many different contexts, where we find that this helps us to maintain and also regulate the output, the long-term output. From the simulation, you can see that not only have we managed to control our steady state value, either being very high with very little feedback inhibition or very low with very strong feedback inhibition, but we have also managed to get a certain characteristic time course. And this is, of course, also the main point of the exercise as on the assignment, where it is thought that it's not only about steady states, I should say, but it's also about time courses, namely the way in which systems react to changes. Right? So you remember in that physiological model, there was this artificial situation where the glucagon hormone was switched on in order to check for a transient response. But you know that in vivo, we have something very similar when we, for example, have a big meal. Intake a lot of sugar and a lot of glucose is set free, so we add a lot of sugar to the blood, and that sets off a cascade of reactions which are typically feedback inhibited, which then lead to transient responses. So one question is, can you actually get these transient responses mathematically? And if you look a little bit into the depths of MATLAB, there's also a function that helps you to solve sets of differential equations. Not just the steady states, but to get the complete analytic solution of the whole set of differential equations. So it means anything that you could predict as a time course. And we have actually looked at one in our exponential growth model previously, in the exponential bacterial growth model. If you try to do it, the corresponding function is called dsolve. You can see if you can find it. Dsolve can be used to solve sets of differential equations. However, there's a very sad story here, namely, you can only solve the current model if you set the feedback inhibition to 0. As soon as you incorporate the feedback inhibition, as soon as you have a feedback of the second variable on the first one, MATLAB symbolic solver, and also, of course, all other mathematics fail to give you an analytic solution that holds for any circumstances. That's why we must complement these things that we know from analytical solution with simulations like the one that you have shown here. If I just point to the simulation again, and Rob has described it already, so I only can summarize which one is the first variable, is actually the blue one. So you can see that this model, from its initial conditions of 0.1 that we used here for both concentrations, has a very strong rise in the first variable. And because the first variable is converted to the second variable, it is followed with some delay by the green function, which is the second variable, which also rises, but you can see with a characteristic delay. The difference between the two is characterized, of course, by the rate with which concentration number one is converted or is converted to concentration number two. A second thing that you can see, both variables overshoot. They show this overshoot, they go through a maximum. So initially they go too high and then they are being pulled back. Why are they being pulled back? Well, you can guess why variable 1 is being pulled back. Because inhibition sets in. Variable 2 rises, and the more of variable 2 we have, the more inhibition we have, such that at some point the initial rise in variable 1 will be overcome and will go through a maximum turn into a lowering, into a diminution of its value. And this then has an impact, of course, with some delay on the second variable as well. If you have too little of the first variable, of course, also the second variable will be less, however, with a delay. And you can see in some sense also the second variable looks like a damped version of the first one. It's not as high as the first one, and it goes slower up and down. So in effect, we have a smearing out effect here. The second variable is like a smeared out version of the first one. And together, they then set on for a compromise, which is this steady state value, for which they finally settle down. There's a lot more that we can say in this type of systems. I stop here for the brevity of time. I just suggest, if you are further interested, look at either Goodwin's book or other material on that type of thinking, where a concept that comes from engineering, namely feedback inhibition, is now refound, so to speak, rediscovered under different disguises, namely in terms of interactions that form feedback loops in, say, signaling pathways, in metabolic reaction sequences, but also in hormonal interactions and in neural interactions, definitely also there. And here you have learned how to mathematically set up a description of this effect and how you can then study it before you go and do further experiments, because now, of course, changing parameters, you can make all sorts of predictions. I don't know which one we can try. You can try to change parameters, or you can expand the equation and simulate it again and find its steady state equations. We hope that these exercises should help you to complete the assignment without any further problem. There should be nothing apart from the things that we have discussed here that are necessary to do the assignment. You have seen the plot, the function solution, the symbolic solution, and the simulation of the model. And of course, you are more than welcome to experiment now with the code given here, or those that you write yourself, and expand these things and use it for other systems, particularly if you have your own research interests where other questions come into mind.